know how good the line is and how big figures I can actually transmit. So the talk is on some recent developments in theory, and the main focus will be how to calculate interesting features of large magnetic molecules. And to give you an idea where I sit, so this is my hotel room, and I turned the TV screen with the help of an HDMI cable that I bought recently into a pretty nice office. Okay, as I said, our group investigates magnetic molecules, and there's a recent review on certain topics. I've taken out a couple of slides on what interesting molecules are around. For a theorist like me, what it boils down to is, in the end, you want to model your spin system, and in the simplest model we can think of, maybe simplest realistic model, that would be a Heisenberg model together with a Zeeman term. And if you follow my mouse, this Heisenberg term, if you're not so familiar with this, contains spin operators that describe spins sitting at certain vertices, here labeled with I, or the red one with J, and they interact with an exchange interaction that I denote with a capital Jij. So in my sign convention, a negative J would denote an anti-ferromagnetic interaction, and a positive J would denote a ferromagnetic interaction. And in the ground state, of course, the ferromagnetic spins would, classically speaking, like to point parallel, whereas anti-ferromagnetic would mean classically pointing anti-parallel. And the second term describes the interaction of all spins with the external field. And this is, of course, a rather simplified Hamiltonian, so they all have got the same G factor. G could even be a tensor. We leave that out for the moment. Good. So we have a model with which we want to describe such nice bodies as this capillarate, icosahedron, or some other interesting molecules that you come to me to model them. Well, if you want to model that, we have to solve the Schrödinger equation that's given here. And usually after my quantum mechanics lecture, I ask the students, after we have solved the harmonic oscillator or the hydrogen atom, why at all do we solve the Schrödinger equation? And usually it's, after all the problems, interestingly, rather hard for them to answer this question. So here's the answer. Of course, also in magnetism, we need to solve the Schrödinger equation in order to obtain the energy differences, and of course also functions that we need for all the spectroscopy that we do, EPR, inelastic neutron scattering, and NMR. And of course, second point, we need to solve the Schrödinger equation in order to set up thermodynamic functions, and the main function that we need is the partition function. From that we can usually calculate magnetization and susceptibility as well as heat capacity. And the third reason why we want to solve the Schrödinger equation is that if we have solved the stationary Schrödinger equation, we easily can solve the time-dependent Schrödinger equation, and we would need this for pulsed experiments, for instance, or in order to simulate quantum computing or thermalization processes. Okay, whatever you are after, in the end, your Hamiltonian always turns out to be a very big matrix. And if you now look at this molecule on your left-hand side here, this is a very old one, a famous one, so-called ferric wheel, where 10 iron 3 spins form a ring. And since iron 3 has got a spin of 5/2 in this molecule, the dimension of the Hilbert space is roughly 60 million. And this is because every single spin has got its single spin Hilbert space of dimension 2s+1, which is 6 for a spin 5/2. And since we have 10 of those, the total space, Hilbert space dimension is 6 to the power of 10. So if I was now in a real meeting, I could ask you, what's the biggest matrix that you ever diagonalized? Okay, I can't see you, I can't hear you, but I can guess, okay? Say you diagonalized a 2x2 matrix maybe in high school, and maybe a 3x3 matrix in your first semesters. And then some of you might have diagonalized bigger matrices on a computer, and the biggest we can diagonalize nowadays exactly, meaning we want all eigenvalues and all eigenfunctions. The biggest have a dimension of roughly 100,000 by 100,000. Okay, I don't argue about a factor of 2, but this is the biggest we can do. And if you compare this to 60 millions, you easily see is that 60 million is way beyond 100,000. So the question is, can we evaluate the partition function without diagonalizing the Hamiltonian H? Okay, beta in front of the Hamiltonian here in this equation is the inverse temperature. So physicists use beta equal to 1 over K Boltzmann temperature. So can we approximate this function without diagonalizing the Hamiltonian? And the answer is yes, we can. And this is the plan for today. I'm pretty sure that I can't run through all of this. This doesn't matter. I took out a few slides anyway, but let's go to the major point. And the major point is that since the late 80s, we know that we can approximate traces. So remember, the partition function is a trace. We can approximate traces by means of expectation values with respect to a random vector. So a random vector is a vector that has coefficients in front of the basis functions that are random. And there are various ways to do these random coefficients, and I choose a special way, namely so-called Rademacher random vectors, and there these random coefficients are just plus minus 1 randomly equally distributed. And this approximation is astonishingly accurate, and it's better for bigger Hilbert space dimensions. So bigger is better. Usually bigger is not better if you think in terms of quantum problems, but here the accuracy is going to be better. So, but the operator that we have in the trace is this exponential of minus beta h, and this is a problem by itself. So we attack this by assuming we can develop this into a Taylor series that's given here, and we look at each term separately, how it acts on the random vector. So 1 on the random vector gives the random vector, h on the random vector gives a different vector, and h squared gives another vector, and so on and so forth. We can do this, say, several times, usually order of 100. So we obtain 100 linearly independent vectors, and they span a small subspace of the originally very large space. This space, the small space, is called the Krylov space. And what we do now is we diagonalize the Hamiltonian in this small subspace. And then the partition function can be put together as given here, namely as the expectation value with respect to the random vector. And since we diagonalized h in the Krylov space, we can insert the spectral representation into this equation and in the end obtain this sum. Okay, here epsilon n are the eigenvalues of the Hamiltonian in the Krylov space, and n of r, these cats here, or bras, they are the eigenstates. And these are approximate numbers. Nevertheless, putting them together gives a very good estimate of the partition function. And then an observable, such as the magnetization, would then simply look like this. Okay? The most important thing at this point is that you say, wow. Okay? Although I can't hear you, just say wow. Because what it means is we can replace a very complicated trace that we cannot actually calculate because the dimension of the space is too big. We can replace this by an expectation value with respect to one random vector. And the question, is this good? And I say yes, usually it's good above certain temperatures. And if you want to improve it, you average over many random vectors. So the idea is a bit related to Monte Carlo methods. And here in this averaged presentation, it's usually called finite temperature Lanzos method. So I give you two examples. Here's the ferric wheel that I showed you. Remember, dimension 60 million. And if I do the random vector business and I just pick one random vector, then I obtain these light blue spaghettis. So every spaghetti is an expectation value of this differential susceptibility versus temperature for just one random vector drawn from Hilbert space, okay? And you see above roughly 10, temperature 10 in these units, it's good. And below it's fluctuating. But if I average over 100 of these vectors, this yields the dots, then I see that I obtain a curve that coincides with the exact curve in this case. So we can do, for the ferric wheel, although it has got Hilbert space dimension 60 million, we can diagonalize this exactly using SU2 and point group symmetries. This is a tedious way to do it, but in this case it works and gives us a nice chance to compare this approximation to an exact result, okay? And on the right-hand side is the same for specific heat. And let me jump to a second example. This is the icosy dodecahedron. It belongs to as a molecule to the class of caplarates. These are polyoxometalates. And what you see here as the red dots or spheres are the sites of the spins, and they are connected with four nearest neighbors. And the whole body is called an icosy dodecahedron. It's related to the Kagome lattice, by the way. So the Hilbert space dimension, if the single spin would be 1/2, is 10 to the 9. And you see that here, a single vector is actually sufficient to reproduce or give you the observables of heat capacity as well as susceptibility. This is astonishing. I mean, depending on what the coupling really is, this could mean that since your squid measures only above 2 Kelvin, that a single vector would yield all that what you need. This is an amazing method. So let me switch to what we can do with that. Okay, what can we learn? And here's a somewhat little bit older result, gadolinium 7, for which we investigated the magnetocaloric effect. And let me show this slide as a reminder what the magnetocaloric effect was. This effect means that a magnetic material changes its temperature if you sweep the field. And on the left-hand side, you see straight lines through the origin, and these are curves of constant entropy S as in the TB plane. So if you have an isentropic process, a process of constant entropy, and you start here on the blue line, which is at a certain field and temperature, and switch off the field, then your system would ideally run down the isentrope in an adiabatic process, and with that you would obtain a single shot cooling. That's, by the way, how Guillaume won his Nobel Prize in the 30s by performing such an experiment with a gadolinium salt, and he was the first to achieve sub-Kelvin temperatures. You can add 2 isotherms to this graph, and then you obtain a full Carnot cycle that you can actually use in a fridge or in a heat engine. Okay, the material that we investigated first is this centered ring of 7 gadoliniums, and they interact with 2 exchange interactions, one around the ring and one of all with the central gadolinium ion. And gadolinium has got a spin of 7/2. That's a very large spin. And as often done in our community, we don't know the exchange interactions beforehand, so we fitted those to the observables that you see on this slide. Magnetization, specific heat, and susceptibility, and in the lower right corner, entropy. Entropy is not an observable. It's usually calculated via Maxwell relations from the specific heat or the magnetization. So our set of J's fits the data well, and I can now give you the major story. The major story is we can relate the low-lying density of states to the shape of the isotopes. The isotopes were straight lines through the origin for a paramagnet, but for interacting systems, they are very different. So they can be warped and have all kinds of strange shapes. And I show you now how that looks like for the centered ring. To begin with, the upper panel is confusing, I suppose. So maybe you switch to the right, where the colored Zeeman level scheme is shown. This is maybe familiar to you to know. What you see is, for small b, the singlet is the ground state, and then it's taken over by the triplet, and then maybe the s equal 2 constitutes the new ground state. And what I show on the left-hand side is not levels versus B. So here, this is not energy. What I show is the levels as function of the distance to the ground state. So the excitation energy. I always define the ground state as 0. And then this crossing would mean that the singlet in this graph goes up after the crossing, okay? Why is this good? It's good because you can now see by eye inspection what the density of states above the ground state is. So there's a certain high density of states here, then there's a low density here in this shaded area, there's another high density of states here, and then here is the saturation field, and above is the low density of states. Now if you move down to the lowest panel and look at the right curve, a red curve, if we start here, say above the saturation field, and we switch off the field, then we enter a region of higher density of states. And to stay on the isentrope, which means entropy constant, and entropy, maybe this is an important help for an understanding. Entropy measures the number of effectively occupied levels. So if you enter a region of higher density of states, then you need less temperature to occupy the same number of levels. And we go further down the field, we enter now a region of low density of states. Then you need a higher temperature to occupy the same number of levels. So this curve kind of maps the low-lying density of states, and turning the whole story around, this would offer us an interesting means to qualitatively understand the density of states for materials where we can't calculate it and don't know it. Yeah, you have to perform a cooling experiment, and that gives you an idea of the density of states. Low, high, low, high. Okay, that was the first example. Let me move to the second. I keep the second short because I reported on this a bit at the APS meeting in Los Angeles. But this story is very interesting because it shows that the magnetic molecules that we investigate may exhibit features that we usually investigate in extended 2D or 3D or maybe 1D, but infinitely extended systems, so-called quantum phase transitions. And this nice molecule shows a quantum phase transition. So it is a ring system where you have alternating gadolinium and iron ions, both valency 3, so this is a spin 7½ and the iron is a spin 5½. And we set up a model that includes a nearest neighbor exchange interaction that will turn out to be ferromagnetic in the end. This is J1, so it's between irons and gadoliniums and irons and so forth. And then we also assume that the irons interact with their neighboring irons with a small interaction J2 that in the end will turn out to be anti-ferromagnetic. So this is a molecule of Annie Powell's group, and she approached me with the data and asked the usual question that you hear often as a theorist: can you fit the data? And as you know, the answer is yes, we can. But it's not so easy, because you know that 10 irons have already a Hilbert space dimension of 60 million. Now we've got 10 irons and 10 gadoliniums, okay? then the total dimension is 10 to the 16. There's no way to do anything with this finite temperature Lanczos, but there are other methods such as high temperature series expansion, quantum Monte Carlo, or classical Monte Carlo, because spins 5½ and 7½ are big spins. So the summary is, yes, we can fit that, and the interactions are ferromagnetic 1 Kelvin and antiferromagnetic 0.65. And in the subspaces belonging to larger total spins, we can diagonalize the Hamiltonian exactly, taking these J values. For instance, here is the space of S equals 60. That's the maximum spin. And there's only one level with its M degeneracies in that space. And if you look very carefully at this graph, you see that the subspaces with smaller spins have a gap towards with respect to this level. And this told us that this nice molecule, here is the ring wrapped on a torus. That's how the molecule really looks like. This has got a spin of S equals 60, and that was for a long time the largest spin ever observed for a single molecule. Well, the interesting features of these molecules arise if you start from this S equals 60, which you easily get if you assume that we have only J1. So then this is all ferromagnetic, the nearest neighbor interaction, and that's clear, all spins align. But now you switch on J2 carefully, and it's clear J2 counter acts against the ferromagnetic interaction at a certain value of J2. A new ground state will take over. But what happens at this point where the crossing occurs is that, as you see here, maybe on the right-hand side, many, many, many levels cross at the same ratio of J2 and J1. And this ratio is called alpha. And at this critical value where they cross, there's a massive degeneracy. If this all were spin 1/2, then 50% of all states would be in the ground, would be the ground state. This is an amazing behavior. And this gives rise to a so-called quantum phase transition. This is a non-analytic behavior of thermodynamic observables at T equals 0. And you see that our molecule, although it's not right at the critical point, but a bit left of it here in this alpha, on the ratio of J2 over J1. But since we are at an elevated temperature, it behaves as being almost critical. And you see this here in the isothermal entropy change, both curves for the real system, that's the solid curve, and for the critical system, that would be right at this critical ratio, these curves are the same. Okay, I hurry up, give you a major message here with these slides. Many of you work on single molecule magnets, and they are anisotropic, and the warning is the convergence of this random vector method, also called finite temperature Lanczos. The convergence is somewhat worse, and it has to do with the fact that symmetries have gone. There's basically no symmetry left except for one, namely time reversal symmetry. We use this, but this is a technical aspect. Again, the message is yes, we can. And here I show you what this means. This is a molecule, or a sketch of a molecule used in Thorsten Glaser's group. It's an hourglass molecule. And fictitiously, I assume antiferromagnetic and ferromagnetic interactions here in the triangles, and the interaction to the center is always antiferromagnetic, as it is in Thorsten's molecules. And I assumed an insane, easy access anisotropy at the manganese 3 here. And what I want to show you is, first, the dashes are the approximation, and they are on top of the exact diagonalization. This is possible. Hilbert space dimension is 62,000, but it only takes hours to make the approximation compared to days to do the real calculation with the exact diagonalization, because you also need to average for the powder. And you can stick to a notebook compared to a supercomputer, what we usually use for the exact diagonalization. Here's another molecule that is kind of fictitious. I guess I think I know there's a molecule from you and Brechen's group of this kind. So assume we can make a molecule of manganese 3s where we have 12 on a ring, and they have parallel uniaxial anisotropies. And I again assume that the interaction is ferro or antiferro, and we can diagonalize this in this approximate fashion. although the Hilbert space dimension is 244 millions. And here, the new method yields results such as the magnetization curve in a few days compared to impossible. Or you can have the field aligned perpendicular to the uniaxial system. Then all symmetries are gone, basically. And again, we can do the magnetization curve for such a massive molecule. Okay, I modified my APS talk by one slide because several of you talk about decoherence. We also have a recent work on decoherence that actually, I see the warning, yeah, I will be ready in 2 minutes, that actually addresses a situation of Andreas Heinrich's group where they put two atoms on a surface and they form a magnetic dimer. Both have spin 1/2. And here's a level scheme. They have got the singlet and the triplet with the Zeeman splitting. And what they now investigate is whether they can install or initialize a so-called clock transition. This is here now transition A, where you linearly superimpose the two m equals 0 levels. And they measured how this decays. So what's the decoherence time of this? And we did the same by running the full Schrödinger equation for the dimer with a small, with a small surrounding of environmental spin. And this is developed in time according to the time-dependent Schrödinger equation. And then we can measure the reduced density matrix of the dimer system. This is what you would measure if you would measure the dimer. And then you see that scenario A, namely the clock transition, that decoheres much more slowly compared to the other superpositions you can build. Okay. Kagome, I skip. You can read all my talks on my webpage. They are all online. This one and the original APS talk, and then the one I gave yesterday at Colorado State in Fort Collins. Okay, with that, I'd like to sum up, acknowledge my nice collaborators that I have the pleasure to work with. Some of them you see here as pictures. And I'd like to thank you for your attention. And as you might know, I run a community webpage. If you want to be listed there or send your highlight, feel free, do it. I put it online. Thank you so much.
Okay, thank you, Juergen. I can tell that many people are applauding right now, but we can't hear them. We've received several questions here. We've got one from Talat Rahman. So from where do you obtain the parameters for your model system?
Okay, there are two answers. Usually we set up a model, so you need to know the model in order to fix the parameters. So say you are sure that this is a Heisenberg with very small anisotropy, then we fit this to observables. This is method one. The second is to use so-called ab initio methods, such as DFT or beyond Hartree-Fock methods. They might give you the J's, but very often this is first a big calculation, for instance, for lanthanides, and second, so far the accuracy is not that good, and it has to do with the fact that magnetism is a low energy feature in condensed matter physics. Our energies are, so the couplings are Kelvin, that is milli electron volts, whereas chemical energies are much bigger. So it's very, it's a tough job to get these small numbers from so-called ab initio calculations.
Okay, thank you. Another question, this one's from Jia Chen. In the random vector method, do you need to store the Hamiltonian matrix in memory? If so, how can we do that?
Okay, again, two ways. You can store the Hamiltonian as long as it fits into memory, okay? This is not much what you can do. Okay, depends on the computer, okay? We investigate the Kagome lattice that I didn't show you. That's this one here. And we can do this for up to 42 spins, which is a Hilbert space of, let me guess, 10 to the 12 or so, okay? And we store the Hamiltonian, but it's stored on 3,000 nodes of a supercomputer, okay? This is way too expensive for normal things. We have a second version of the program that calculates every matrix element on the fly when you need it, okay? This means that you might have to calculate the matrix elements again and again and again. I mean, as often as you do these Lanczos steps, but this is much cheaper. Then you need to store only 2 vectors. So the Lanczos method is iterative, and all you need is 2 vectors of the size of your Hilbert space. And this is much cheaper than to store the Hamiltonian.
Okay, thanks. Okay, so this one's from Steve Blundell. How large a system, in other words, Hilbert space, can you use the finite temperature Lanczos method?
Yeah. So as I said, you need 2 vectors, and they have to fit into your run. Okay. We go up to 10 to 11, and this is pretty big already. This corresponds to the 42 spins 1/2, for instance, or we can easily do this manganese 12, this fictitious manganese 12 ring, or we actually did the real manganese 12 molecule with this method. But beyond 10 to the 11, that's complicated for several reasons. You need a supercomputer to store these vectors and actually to treat them. But you also run into problems of accuracy. You have to go from, say, double precision to higher precisions in order, for instance, to be able to normalize these vectors.
Mm-hmm. Thanks. So Mark Peterson asks, can you clarify whether any of the laptop-based diagonalizations used point group symmetrization along the lines of Marshall-Luban versus Lanczos-like methods, or were both used?
Okay. Hi, Mark. I hope I didn't say too bad things about DFT. So we use symmetries whenever we can. So you can also, for the finite temperature Lanczos, use the irreducible representations that are available to you. So very often in the Heisenberg model, for instance, SZ is a good quantum number, and this is a very simple symmetry to implement in these Lanczos calculations. And then on top of this, a point group is also easy to implement. SU2 together with point group is very, very complicated. And that has to do with the fact that the point group operations kind of destroy your coupling scheme or transform your coupling scheme into another one. And in order to keep track of this, you need a lot of basis transforms, and this makes the method very lengthy. Does that answer the question?
Okay, thank you. Is this a separate question? Oh, Mark asks, do you think SU2 plus symmetry has been implemented in general?
SU2 can be implemented pretty, I mean, here are 2 of our references, yeah? SU2 can be implemented for Heisenberg-like models. I mean, what you need is spin rotational symmetry, okay? As soon as you have got anisotropy, then there's no SU2 anymore, okay? But if you have got SU2, you can implement this easily. That's implemented in MacPack, a program that many of you use. And that goes back to Zuckerblatt and Eugenio Coronado and Gatteschi, of course. And it's also used, I think, in DMRG by now. We did not implement this in our method because we also want to investigate anisotropic Hamiltonians. So SU2 alone is not the problem, and point group alone is not the problem. The combination is the problem.
Okay, so Mark says thanks. I say thanks. That was a nice talk. We're out of time for questions, and so